So now let's start your presentation. Sto-san, okay.
So, yeah. Hello? All right. All right, so I accidentally told people a bunch of different names for this talk. So I've got all of them listed here. If you see it in the list, then you're at the right place. So I'm just going to start off with a little demo. All right, so that was from a project that I'm calling Ruck Live. It's based on this other project I'm calling. It's a library for Ruby called Ruck. Just to make sure that we're on the same page. So the idea for Ruck came from this programming language called Chuck. I don't know if, has anyone used Chuck here before? Okay, I got one person. That's fine, that's all right. So it's this audio programming language. It's designed for on-the-fly programming. So the idea is you should be able to write the code as it's executing, as people are watching you do this. So it needs to be succinct. And as Rubyist, we can really think of it as a domain-specific language for doing this live coding performances. And specialty is really manipulating time. So, excuse me. So there's some vocabulary I'm going to be using over and over in this talk that I get from the Chuck language. And I just wanted to get this out there first, which is a shred is basically the same as a thread, except it's going to be managed by Ruck instead of by the Ruby program. And a scheduler is the same as a scheduler, except it schedules shreds. And instead of this being like the Ruby scheduler, this is going to be an object inside Ruby that you have control of, and you're going to be subclassing and modifying. And then spork is the same as fork, except instead of forking processes, you're sporking shreds. So just keep these in mind. I'm going to be using these for differentiating between the Ruby equivalents of all the things that I'm talking about. So organizing this talk, first I'm going to talk about strong timing and virtual time. And these are the ideas that I'm taking from Chuck and incorporating into Ruby. And I'm doing that with this library called Ruck. So I'll be talking about how Ruck does that inside Ruby, and then I'll talk about a couple of things that you can do with this library once you have it. So starting off with an example of some Chuck code. The first line is basically saying take this sine tone generator and connect it to the speakers. And then the second line is saying allow 4 seconds to pass after you've done that. So instead of executing, just going to say it goes doo. and then it finishes. So second example is if you want to play a WAV file in Chuck, what you do is you'd create a buffer for the sound file to go into. You connect that to a reverb unit, and you can connect it to the speaker. You run the second command, which just reads that WAV file in, and then you allow 4 seconds to pass. And so that'll play the WAV file for exactly 4 seconds and then stop. And so traditionally, when you think about how long this code takes to run, you'd include like the time it takes Chuck to start up and for it to load all your code from the files. You'd include the time it takes to play the WAV file, and then you include the 4 seconds where it's actually playing. But in Chuck, you're not thinking about real time. You're thinking about the virtual time against which all of your shreds are being scheduled. And so in that case, the load and the creating of those sound generators are not taking any time. It's just the 4 seconds that you care about. And so the idea is that all your code is executing instantaneously. It's not really, but with all the buffering that's going on and things like that, you can usually hide the delays that are being caused by that. So what this means is that it puts the programmer in complete control of when code executes. So if you have multiple threads and you want them to be accessing some shared data structure or whatever, or you want them to be interacting in some way over time, if you tell them both to, I don't know, sleep for 4 seconds and then wake up and do something, and you tell them to do that repeatedly, they're not going to drift apart because Chuck is making this virtual time guarantees to say that it's going to wake up exactly 4 seconds later against the virtual clock. And in real time, it may be a little before, a little bit after, but it's going to be the same relative to one another. So you have consistency and coherency in your code, and you can reason about what's going to happen. So here's an example where you have 2 shreds going. They both load different WAV files, and then they allow 5 seconds to pass. And so what this looks like with a traditional threading model is that you have these 2 threads executing in parallel. The first one does its load and plays for 5 seconds. The second one does load and plays for 5 seconds. Loading those WAV files is going to take different amounts of time depending on operating system caching, all sorts of things. So they're not going to play at the same time. With the strong time model, what you're imagining is that each of those loads are happening at exactly the same time, and they're not taking any time at all. So when they both say allow 5 seconds to pass, since no time has passed in either of the shreds, they're both going to start playing at exactly the same time and stop at exactly the same time. That's the idea. And the way it's implemented is it's actually serializing all the commands that you're giving it. So it does the first load, it does the second load, and then it plays for the 5 seconds. And so this stuff is happening instantaneously, no time is passing inside your code, and then the rest of this is where the time is actually going on. And so the main idea is that time is not passing until you let it, and you're controlling exactly when things happen. So that's the main idea behind Chuck and strong timing. And so the idea was to port these ideas over to Ruby. So the way the RUT code looks like when if you're translating just your Ruby code over is instead of creating new threads, you're calling spork, which is the fork command. It's creating a new thread, but it's on the Ruby scheduler that you're creating. And instead of calling sleep, you're calling shred.yield, which is yielding time on the virtual timeline instead of real time on your CPU. And so the scheduler object is what's actually keeping track of all the shreds they're supposed to be executing and make sure that they are woken up at the right times and making sure that the timeline stays coherent. And when you change various settings on it, everything continues to work. And so after you've created all the shreds that you want to launch, you call scheduler.run, which just continuously executes these shreds in the proper order until all of them have exited. And so I'm going to talk about the scheduler object now, which is really the mapping between the virtual timeline and real time, or anything else really, because by default, the scheduler that comes with the RUC doesn't actually do anything when virtual time passes. So if you have a shred that says shred.yield 2, it's not going to yield 2 seconds because it doesn't know how to do that yet. It basically just says, okay, schedule this for 2 virtual time units in the future. And if anything's scheduled to happen before then, it executes those and then immediately continues on to the one that you have just put to sleep. So this gives you the freedom to really map it to anything that you want. You can map it to real time just by inserting a sleep command inside of there. Or you can map it to like what Chuck does, which is the audio stream in a file. So it's playing back audio and you're manipulating all the objects that are creating sound as they're creating sound. And when you say yield 2 seconds, it's yielding 2 seconds of real time. Or you can do it in MIDI ticks, where the units of time might be the ticks in a MIDI file, which are like divisions of a quarter note, so they change depending on the tempo of the song that you're playing. So this is some way of visualizing what's going on. Is let's say that you have these threads A and B. and thread A does some stuff and then sleeps for a while, and then does some stuff and sleeps for a while, and shred B is doing the same thing. And so it's got these gaps in here which it can really fill with whatever it wants. And so what you put in there could be sleeping, it could be writing blank samples to the file, it could be displaying a blank screen if it's some kind of game or video simulation that you're running, or it can do any of the above, because unlike Chuck where the scheduler is fixed, it's part of the runtime, in Ruck it's something that you can modify as you're going. So the way this is implemented is that every time it's got one of these gaps, it calls fast forward, which is the implementation of how you pass time. So the default implementation, all it does is set its clocks forward by the amount of time that's actually passed, so that after it executes these, it sets the clock forward to here, and then it can execute B2 immediately. But usually what you will do is you'll subclass scheduler and be overriding this method to do whatever you want. So I've got an example where I do this for a MIDI file. So I'm going to run this the first time with this setting as 1, which just means play it in real time. And so this is just a script that I wrote that generates some random chords and then a melody to go over top of them. All right. And then I can change the flag to a 0, which means don't bother running this in real time, just play the MIDI file out and save it to disk instead. And so once I've done that, I've got this MIDI file out here. And it's going to be different this time since I ran it a second time. So that's generated by the scheduler, and the code that's telling it which notes to play and when is exactly the same in both those cases, because they're both relying on the scheduler to provide the sense of time. They don't really care that I'm going to a MIDI file or I'm playing in real time or doing whatever. I could go in there and say, this should play at double speed or this should play at half speed, and the code stays exactly the same because Ruck is managing all the time for this project. And so I've got another example, which is if you use the Chipmunk library with Ruby, it comes with a demo project that looks like this. So this is just a simple game where you got a spaceship running around, you're collecting stars. I've modified it because I didn't like the controls in the original, but other than that, and some extra text in the upper left, it's exactly the same. Or at least it looks exactly the same. What I changed it so that all the internal stuff that has to do with time, like the executing the physics simulation for the ship and all the star collisions, the animation for the stars, the frame rate calculation in the upper left, and even the drawing code, all of that is independent of the actual loop, the graphics callback. And so that's all scheduled by Ruck using events and things like that. So I can do things like if I'm pressing a key now, which inserts delays inside of the rendering callback, and you can see that all the stuff is still executing at the right time, all the animations are still running at the right speed, it's just the game is getting slower. So everything's still happening on time, it's just happening not as frequently. So some of the benefits of Ruck for games, you just saw one, which is that if your game's running slowly, it's still going to be executing all the stuff at the right time. So you get frame rate independence automatically just for using Ruck, because you're thinking in terms of time. You're not coding in terms of the graphics callback getting executed at the right time, or how much time has passed since the last time you called the graphics callback, and things like that. All the timing code is concentrated inside of the scheduler. I'm going to talk about each of these in just a moment, but all the code that you're writing just has to think about what time it would like things to happen, not how much time has passed or any of those calculations. And you get a better separation between the graphics callback and all the other code that would normally go inside of it. And so all the drawing code, well, none of the drawing code is inside of the graphics callback itself with Ruck, because I can just say, wait until the next frame and then draw. So it's all scheduled alongside all the other code that's inside of the scheduler. So this is what the physics simulation code looks like in this program. It basically says Spork loop, which is like Spork, except it automatically inserts a loop block around the stuff on the inside, and it yields this amount of time every iteration. So it's yielding the step size for your physics simulation, which will be like at, I think it's 60 hertz times 6 inside the original game, so I just kept it like that. And then every time that the deadline comes up, it does a step of the physics simulation. So it doesn't matter what the frame rate is because it's going to execute on time, and it's going to happen at the right time. And so the time and code consolidation that I was talking about is that, well, you're not writing code that looks like this, which is just saying, well, what time is it currently? Should I have executed more physics steps before now? If so, execute that many steps. And in a lot of code that I've seen in games, you end up with loops like these all over the place every time you need something that needs to be independent of the frame rate, where when you're using Ruck, all the code that looks like this and all the code that just happens every frame like the drawing looks the same because it's all being scheduled by Ruck. And also you get this nice abstraction where the only thing in the graphics callback is really just telling the scheduler to execute the threads to catch up to the current time. So this code up here is not inside of that callback. It can be anywhere inside your code because you're just spawning a thread to manage this one aspect of your game. So, yes. So one of the biggest differences between what's happening inside the MIDI example and what's happening inside the game example is that for the MIDI one, the scheduler gets to completely control time, where you're just creating a scheduler, adding a bunch of threads to it, and then executing all the stuff until it finishes, and then you exit because that's the only thing that's happening inside your program. But inside the game, you're inside of someone else's callback. So the graphics card is dictating when your process gets to wake up and do its thing. So the question is really like, what do you put in here so that actually works? Because what you really want to happen is you want to be moving along this blue line, which is for every second of real time, you've simulated exactly 1 second of the virtual time, or whatever your mapping happens to be. But you really only have every once in a while you're getting called by these graphics callback, and that's when you get to do your thing. So we need a function that will, whenever we get that chance, catch up and be as accurate as you can and get to that point, because we know we're going to stall for a while and then catch up again. And so what that ends up looking at is that inside the graphics callback, you tell it what the current time is supposed to be. And then the scheduler has a function on it that will just execute threads until it catches up to that point. All right. So that's mostly what I had to talk about today. And yes, are there any questions?
Any other questions?
I think I talked a little fast.
Yeah.
Some of the things that I didn't think that I would have any time to include was going over what the code actually looks like for some of the demos.
I will ask a question. So for the first demo you provide is the real-time editing. Did you edit the code real-time on a demo?
Yeah.
Ooh.
Yeah, that one is. That's probably the most interesting demo right now. So what this looks like, well, the basic mode of operation is that I start this server, which starts a scheduler, and it gets into this loop, where all it's doing is calling that catch-up function, which is run until with the current time over and over and over. So it's not doing any kind of sleeps. It's just checking the time.now repeatedly, saying, is there anything to run? No. Is there anything to run? No. Is there anything to run? Okay, there's something to run. I can run it now. Parallel to that, I have a thread here which is starting an OSC server, which is waiting for packets to come in with just Ruby code inside of a string. And whenever it does, it queues that up for processing inside of the scheduler thread, and then it executes those as shreds. Which means that when I have code here, what I was doing was I was highlighting this and then running it through that script, which was sending it over OSC, over to the main thread. So I created just a bunch of helper functions like measure sync and spork loop, so that I could just highlight it, and then boom, it would go over and get executed at the right time. The nice thing about the measure sync and beat sync functions is that they're pretty simple, because all shreds have their shared sense of now, and they know it's not going to change while it's executing. So if I say time.now, and then on the next line say time.now again, it's going to be different because some real time has passed. But virtual time isn't like that because it's standing still waiting for you to do whatever you want with it. So I can say shred.yield 1.0 minus b clock.now. And so I'm doing modulus saying find basically wait until the beginning of the next beat is all that this beat sync is doing. And then this is doing the same thing with measures of 4 beats. And so I can say measure sync spork loop now, and that won't execute the spork loop, it won't spawn that shred until the beginning of the next measure. So I can really hit the hotkey at any time and everything stays in sync. And that's a little bit harder to do, a little bit harder to do otherwise. Where'd it go? And also this is another one of the features of Ruck that I didn't think I'd be able to get to, which is that when you first create a scheduler, by default it has a single clock against which it can schedule different events. But each of those clocks can also have subclocks that are running in parallel but at varying rates. So what I was doing here, and I can start up this program again, is I was creating a new clock and then adding it as a child of the other clock, so that when I came down here and added the low woodblock sound, by default it's waiting 1/4 of a beat and then waking up and then playing a sound, and 1/4 of a beat and waking up and playing a sound. So I can change the relative rate here by saying wait for the nearest beat and then change that rate to play in triplets instead. And so or I can stop it completely and it'll stop getting any events. So whenever you call the shred.yield, which is what's happening inside a spork loop, you tell it which clock you want to be sleeping against. And so I'm saying use the subclock, not the main clock, so I can change its rate independently of everything else. And so this allows you to have, well, for one, it allows you to stop everything that's on a current clock just by changing its rate to 0. It allows you to have things going at varying rates relative to one another, like if you wanted to make your music sound a little more natural, or you wanted to add swing to your music by changing the rate at which things are happening, you can do that just by changing the rate of the clock that all of those musical events are happening on. And so real time is still progressing at 1:1 ratio to real time, but all the events that are supposed to have that swing added to it can be changed like this. So that is how that works. Yes. And you can do all sorts of great stuff. So anyway, that was that example.
Pretty cool.
So the space example was the other one that I wanted to be able to share. I'm glad I gave myself time to do it. So the game scheduler is just a subclass of the scheduler, like I usually have in every one of my projects, but all it's doing is it creates this catch up function, which is just run until actual now. And actual now is what's returning what should be the current time of the virtual clock, even though it's not there yet. So like in that graph, every time I get a chance, I call that function, and it tries to catch up to where it's supposed to be and execute all the threads as fast as possible. And when this is called, is inside of the draw. So this is just the line where I was making it slower. So I call catch up, which executes all the stuff up to the current time, and then I call this raise all function, which wakes up any shred that's waiting on an event instead of a time. So if you say sleep for 2 seconds, that's different from sleep until this current event is raised. So I'm using that for waking up all the things that are supposed to be drawing to the screen at the right time. And I call it just catch up one more time so that all those things that I woke up have a chance to execute. So at the start, yep.
Oh, any other questions? 日本語でも大丈夫ですよ、多分。大丈夫ですね。大丈夫。
今日紹介されたライブラリを使って何かこうすでにこうゲームを作った例っていうのはあるんでしょうか。
So, have you created some game application using Rack?
How do I do what with the application?
Objective-C?
How do you create the game?
Yeah. No. Did you create it? Did you create some game application using Rack?
Yeah. Yes, the space game was using Rust.
Any other production games?
No, I have not.
No.
No, I haven't made a single line of production code until about this year, and it had nothing to do with Rust.
ということでした。
ありがとうございます。
他はどうでしょう Any other questions? Try your English.
タッカーと言います。すみません、ちょっとあんまり分かってないんですけども、そのスケジューリングは Ruby でやって、その波形っていうのはちょっと OSC っていうのが見えたんですけども、別のエンジンでやっているっていうことでまずいいんですよね。
He wants to confirm that the rack is for scheduling and the sound source is provided by other software like OSC. Is that correct?
Yes, Ruck is just handling the scheduling of when things should happen. Inside the game that's doing the physics library, all the MIDI stuff are all other libraries that I'm using within the Ruck framework. And so I'm creating the programs that schedule using the Ruck, but are operating otherwise completely normal. So.
だそうです。
Hope that made sense.
もう一度いいですか。すみません。ゲームの時は遅れると、だんだん、画面が遅くなっていくんですけども、サウンドの場合はそういうのって、なんか考える、しょうがないと思うんですけども、どう思いますか。
In game or in graphics, the frame rate decreases, but it's なんていうんだろう。わからん。
すみません。いやじゃあそんなに重くなったりは今のところしてないでしょうか。
おお素晴らしい。The question was in-game frame rate is decreased. How about sound? Sound, yeah. If the frame rate is decreased, the sound. How should we handle the sound?
So the way I was doing in the space demo was exactly the same as in the original Chipmunk physics demo, which is just relying on the STL. I think it's STL mixer library for playing the sound. So I'm not doing any of the synthesis inside of Ruck, if that's what you're asking. What will happen to the sound? Oh yes. If I understand the question now, it's that if the sound is actually being affected by changes in the speed of Ruck's clocks. And no, it's not affected. The sounds are just being triggered and then handled separately from outside of Ruck.
なので、音はちゃんと再生されるっていうか、遅くなってもそれなりに頑張って再生するんじゃないでしょうか。っていう気がした。そんなとこかな。いい時間ですね。So now time and thank you for the presentation.